we present to your attention the concept of a multi-stage desalination plant with self-powered solar energy based on film evaporation drums and an average daily desalination capacity of about 22,000 liters of fresh water per day. A key element of the proposed desalination technology is the use of film evaporation drums, which ensure continuous cleaning of heating surfaces from salt deposits, which makes it possible to concentrate evaporated solutions to high values despite the presence of sludge. A rolling rod with a spiral winding ensures the transportation of sludge under the water level in the drum to the place of periodic unloading of the concentrated solution. From unusable water or saline solution, the unit produces dry salt and clean water. With the ability to process toxic wastewater from large desalination plants, the solar desalination plant could help solve environmental problems in preserving warm sea habitats. The equipment of a solar desalination plant is simple in design and can be produced on a mass scale, especially for film evaporation drums, since the main elements in them are thin-walled pipes of large diameter. The desalination plant does not require external energy sources. It is truly autonomous. The operation of a solar desalination plant does not require expensive consumables, which include membranes, filter materials and chemical reagents, as well as special complex and expensive equipment, for example, for electrodialysis. The desalination plant operates in automatic mode, and maintenance of the installation consists of periodically cleaning the surfaces of solar photovoltaic panels and reflective surfaces of reflectors from dust and sand, as well as periodically unloading accumulated salt from the bunker. Multi-stage evaporation allows you to increase the efficiency of using energy received from the sun by 10 or more times. The energy costs for rotating the film evaporation drums with gear motors, blowing air with fans to dry the salt concentrate and changing the position of solar concentrators is no more than 2.5 kilowatts with an average productivity of 2.2 cubic meters of fresh water per hour. Thus, an average of 1.14 kilowatts of electricity should be consumed to produce 1 cubic meter of fresh water. Modern desalination systems require about 3 kilowatts of energy per 1 cubic meter of finished water. Minimum costs are provided by reverse osmosis systems 2 kilowatts. Thus, in terms of energy consumption, the presented multi-stage solar desalination plant is significantly more efficient than even reverse osmosis plants, and at the same time, they do not need expensive membranes that require periodic replacement, moreover, which can only work after careful preparation of water entering desalination. The performance of the installation was calculated for regions with an average annual insolation of 2,700 kWh per square meter, which on average provides a solar energy flow of 740 W per square meter during the day. Using 3 parabolic solar energy concentrators with a reflective area of 70 square meters each and taking into account 10% of the thermal losses, in 3 rotating film evaporation drums installed in the parabolic concentrators, 238 kilograms of steam per hour is produced at a pressure of 500 kilopascals. The length of each film evaporation drum in a parabolic concentrator is 20 meters, diameter is 300 millimeters, the thickness of the drum wall with a light-absorbing outer coating is 3 millimeters. This steam is divided into 2 streams and sent as heating steam to the first stage drum film evaporators, where it condenses and produces secondary steam with a pressure of 430 kilopascals. The resulting steam is then sent as heating steam to the second stage drum film evaporators and so on through 10 stages of each of the 2 multi-stage evaporators. On average, each of the 20 evaporation drums produces about 1,000 liters of fresh water per day. Thus, the average total output of a solar desalination plant is approximately 22,000 liters of fresh water per day. The length of the evaporation drums with a diameter of 480 mm is 6 meters, and the wall thickness is 2.5 mm. Cleaning the heating walls from salt deposits is carried out with a heavy rod with a spiral winding, which rolls when the drum rotates, moving the fallen particles to the place where the concentrate is unloaded. A gear motor is used to rotate the film evaporation drums. At night, the rotation of the drums of multi-stage devices is ensured by a wind engine through a differential mechanism. The liquid level in the film evaporation drums is maintained by supplying feed water using a float valve. Secondary steam from the last 10th stage with a pressure of 150 kilopascals is sent to an air heat exchanger, where it is condensed, and the heated air is sent to a conveyor line, where the brine concentrate is dried to a dry state. Dry salt accumulates in the hopper. High steam generation pressure in film evaporation drums located in parabolic solar concentrators is achieved by increasing the pressure in a 30 cubic meter feedwater tank using an air compressor. Periodic drainage of the salt concentrate from the film evaporation drums into buffer tanks that supply the concentrate to the conveyor for drying is carried out by the opening signal of the solenoid valve. A plate heat exchanger is used to cool the resulting water condensate and heat the source water supplied to the film evaporation drums. The cooled condensate enters a 100 cubic meter tank located below ground level. The solar desalination plant receives energy from solar photovoltaic panels and is not dependent on external power supplies. The total cost of the desalination plant is estimated to be about $230,000. The design of heating equipment is based on known physical processes of heat transfer and is easily amenable to computational analysis.